So let's start with the correlation coefficient. Now this is a very important analysis to be done when there are variables which have some relation, and that we have to identify that how closely they are related. So let's start with the Jupyter notebook. Now first, as we discussed in the earlier tutorials, that we can write kind of a heading or a title. Already we have given at the top, that is correlation coefficient. Then you can always start with this whatever heading that you want to give, correlation between two variables. Then you can see that the variables within a data set can be related to for lots of reasons, and this could be like one variable could cause or depend on the values of another variable. One variable could lightly associated with the another variable. Two variables could depend on a third variable which is unknown. It can be useful in data analysis and modeling to better understand the relationship between variables. The statistical relationship between two variables is referred to as their correlation. So whatever relation they have, that relation between the two is known as correlation, right? So let's, because this is all remark, we can run it. No effect will be there. Again here also no change, no effect. So then the third is that a correlation could be positive, negative or neutral, as we have read in the tutorial. So it could be positive correlation means that both variables change in the same direction. Neutral correlation means that there is no relationship in the change of the variables. And then negative correlation means that variables change in the opposite direction, right? So again we can run it. Again there is no, because it is all remark. Now there is some data set that we have to take into account. So before we look at correlation methods, let's define a data set we can use to test the methods. We'll generate 1000 samples of two variables with a strong positive correlation. The first variable will be random number drawn from a Gaussian distribution with a mean of 100 and a standard deviation of 20. The second variable will be values from the first variable with Gaussian noise added with a mean of a 50 and a standard deviation of 10. So this is what our assumption on the basis of which we are going to create our data set, right? Again we have run it, no effect. Now next is that we will use the random random function to generate random Gaussian values with a mean of 0 and a standard deviation of 1. Then multiply the results by our own standard deviation and add the mean to shift. This is just an explanation so that you can understand it correctly. So the values into the referred range, and the pseudo random under generator is seeded to ensure that we get the same sample of numbers each time the code is run, right? So again we can run it, no effect. Now we are going to import the relevant libraries. As we discussed about the libraries which we require to import NumPy, and along with that import mean. So from NumPy is the main library, and from there we are importing mean. This is a sub library of NumPy. Then similarly from NumPy import std, that is standard deviation. From NumPy random, it is a sub library of NumPy, and from that we are importing random, RANDN. And then from NumPy random import is seed. Then matplotlib we have to import as pyplot. So this is what we have to import, because we are going to use these libraries for our various computations. Then again remark that seed random number generator. So we can generate the seed number. Seed is equal to 1, that is within bracket 1. Prepare data. So data 1 is equal to 20 into, this is the way you have to write the codes. And this you have to, right now you can understand with this, but definitely if the data changes there, you can write accordingly. Data 2 is data 1 plus 10 into random 1000, because 1000 is the sample set that we have taken, plus 50, right? So to summarize it, we can print data 1 mean is equal to percentage. This is the way we have to write our text or code for getting the proper result. So this 3f, then standard deviation, again decimal 3f, and then mean data 1 and then standard data 1. Similarly for the second data set. And then when we go for pie plot with the help of this matplotlib that we have already imported, so we can get a scatter plot with the data 1 and data 2. These are the two variables that we are considering. So when we go for show pieplot.show, you will see that you will get a scatter plot, right? So it is still in process. Now this is star which you are seeing means that this is still under process, and once this process is over, the number will come which will be the next number from the previous one, and then you are going to get a graph scatter plot like this. Now you can see the data 1 mean is equal to 100.775 standard. That is whatever we have given as the data that we have taken. Accordingly, this is a kind of a additional information that you are getting. And data 2 you are getting mean is equal to 151.050. Why this is 3? Because we have given 0.3 as the decimal places. Similarly here also, right? So this is the way this text once or twice you will see it, and then definitely you will remember all this. So you will start writing the code accordingly. And this is the data 1 and data 2. So and these are the various data points which are appearing here on your graph. This is scatter graph, right? Now a scatter plot of the two variable is created, that we have seen, because we contrived the data set. We know there is a relationship between the two variables. This is clear when we review the generated scatter plot, where we can see an increasing trend, and it is increasing because the data points are like that. That is why the graph is going from this lower side to the upper side, right? So this is how the scatter graph can be drawn. Now we are going to find out the covariance. So again the new heading has been given, covariance, and you can see that variables can be related to a linear relationship. This is a relationship that is consistently additive across the two data samples. This relationship can be summarized between two variables called the covariance. It is calculated as the average of the product between the values from each sample, where the values have been centered had there been subtracted. So we can calculate the covariance matrix for the two variables for our test problem. Now the two covariance that we are going to calculate is between the two variable is the numpy random import random. Again, since we've already done, we need not do it, but if we do it, it's fine. From numpy dot random import seed, from numpy import COV. The COV is covariance, seed random number generator. And again seed 1 we have taken, data 1 and data 2, again the same type of formula have been created. Calculate the covariance. Now covariance is equal to covariance of data 1 comma data 2, because there are two data sets, two variables are there. When we print covariance, you will see the result will be available. So now we can run it. Once we run it, you can see it will continue, and once the process is completed, you will get these types of covariances. Now 385.3329, 389.75, then 389.75 and 500. Whatever is the calculation. Now mind you, one very important thing is that as many times it is not necessary that all the time you get the same result. It may vary because of various reasons. So because it is all approximation, but approximation is quite close. So this is the way you can calculate the covariance between the two variables, that is data 1 and data 2 that we have seen. Right. Now we can also calculate the Pearson's correlation. Now Pearson's correlation coefficient named after Carl Pearson, who the person who has created the Pearson correlation, can be used to summarize the strength of the linear relationship between the two data samples. Now the Pearson's correlation coefficient is calculated on the covariance of the two variables divided by the product of the standard deviation of each data sample. It is the normalization of the covariance between the two variables to give an interpretable score, right? So this is how, this is just an explanation. I have tried to make it as explanatory as possible so that you can understand. Otherwise it is already covered in the theoretical part. So calculate the Pearson's correlation between the two variables. That is, again we import the random and seed, and this is now SciPy is again a new library which we are, so from SciPy dot stats is the statistical statistical calculation you need to do. This is the sub library of this. Import Pearson R is the correlation, and Pearson is the name of the method that we are going to use here. So seed random number generator, seed 1, prepare data, and then data 1 is, again you can see the formula is by and large the same. Data 2 is data 1 is equal to 10 into random plus 50, same formula. Calculate Pearson's correlation, and correlation dash is equal to Pearson correlation, data 1, data 2. So we are trying to find out the relation between the two. So print Pearson's correlation, and again we are taking only 3 decimal points, and this is the correlation which is getting calculated here. So this is how the output will appear. Now again we are going to run it. Once we run it, you can see you will get the calculation. Again the process is on, so star is appearing. Once the calculation is completed, the star will go and the process number will appear, like 9 has come in. And you can see the Pearson's correlation is 0.888, right? 0.888. Now, if you remember, we discussed about the correlation which should be from -1 to +1. It cannot be more than 1. It cannot be less than -1. So if it falls with, and this means that there is a very close relationship. 0.8. That means it is almost close to 1, which means that the relationship between the two data sets, two variables, is very, very close, right? So this is how you can calculate the Pearson's correlation. Now there is another method of correlation calculation, is the Spearman's correlation. Let us try and do that and see that is there any difference between the two or not. So again this is the heading. So two variables may be related by a non-linear relationship such that the relationship is stronger or weaker across the distribution of the variables. Further, the two variables being considered may have a non-Gaussian distribution. Now Gaussian, what is the Gaussian distribution? That you can refer the tutorial, or maybe Google it, or refer some book on that, right? Because the details we cannot discuss here at this stage. Now in this case, the Spearman's correlation coefficient named for Charles Spearman. Now this man has also done something on this correlation, so that is why his name is appearing here, and his name was Charles Spearman, and can be used to summarize the strength between the two data sample. This test of relationship can also be used if there is a linear relationship between the variables, but will have slightly less power. For example, may result in lower coefficient scores. Now again you can see the same, all those things are same. So definitely when you are seeing it again, so you'll definitely remember it. So from NumPy random, import random, then import from NumPy random, import speed, then from SciPy stats, import spear. Now earlier we imported the Pearson's R. Now we are importing the Spearman's R, because now we are calculating the method of Spearman, and R of course is common because R indicates the correlation. So again formula is same, seed 1, only thing that Spearman has changed from Pearson. Data 1, data 2, again the same formula that we have used earlier. Calculate the Spearman's correlation. Correlation is equal to this. Here again you can see the same difference. Spearman's name has come in. Data 1, data 2, and again say same example, same code. Only thing that name has only been changed in this. Now when we run it here, you can see again it will be under process, and now we are getting 0.872. Now this 0.872, and here we got 0.888. So the difference is not much, although there is some difference which of course will be there because the methodology is different, but this indicates that the relationship is by and large the same, and the result also gives you that. So this is how you can calculate the correlation between the two data sets, right? So this is our correlation coefficient. This is very, very useful, so you must remember and practice it. Thank you.